Faraday's law here, and basically Faraday's law is going to a formula that's going to relate the amount of electrons. When you think about amount of electrons, hopefully you think about, when I say the word amount, you say moles. Okay, so the moles of electrons to basically the amount of a substance being produced or being reacted. Okay, so current, first of all, is the continuous flow of electrons. So when you turn on a light switch or whatever the case might be, you are flowing electrons, of course, and that is what's giving you the light in that case there. It is the amount of charge measured in coulombs that passes any given point during an interval of time, so that's measured in seconds usually. Current is measured in amp. 1 amp is basically equivalent to 1 coulomb per second is what that is equal to. We're not going to really worry about that too much. We're going to use this in a formula here, like I said, and the formula here will be coming up here. But Faraday's law, basically, like I said, is the amount of substance, so the amount of reactant or product related to the amount of electrons that we're using. Okay, it is basically, to summarize this, the amount of a substance reacted or produced in electrochemical. So electrochemical reaction is directly proportional to the amount of charge that flows through the circuit. So when we talk about amount of electrons and amount of reactions and reactants and products, we're really talking about here nothing more than stoichiometry. Okay, that's what this is. But we're going to use the amount of electrons in part of this stoichiometry equation here. If you think about, well, I guess I should just wait here and we'll talk about that in order here, but this didn't turn out very well here, but on yours it says this here. So N with the little e electron there, that is the amount of electrons. So that would be your moles of electrons or amount of electrons here. So you can write that down, moles of electrons, okay, is your Ne there, amount of electrons. I is the current that passes through, and that's measured in amps. Okay. I stands for the current that passes through. T is the time. Oops, I guess I shouldn't do that maybe. T is the time, and of course that is measured in seconds. Okay, so time, T, seconds, and F is his Faraday's law constant. This number is given to you there, but Faraday's law constant is 9.65 times 10 to the 4 coulombs per mole here. Okay, and like I said, coulombs is basically 1 amp per second. So amps per second are built into that. Okay, the coulomb takes care of the amps and the seconds here kind of thing, and the moles, of course, gives you the moles, matches up with that. So everything kind of cancels out nicely there, but it is coulombs per mole for Faraday's law. So that's the formula we're going to use to relate the amount of electrons that flow through, this circuit or this voltaic cell or electrolytic cell at any given time here, basically. All right. Faraday's law constant is the molar charge of electrons, and of course, once again, 9.65 times 10 to the 4 coulombs per mole. Okay. The amount of electrons can then be used to determine if the amount of the reactant or product involved in a half reaction. So of course, if you think about where are we going to get electrons, or where do we have electrons in equations, we don't have electrons in equations for like net cell reactions. Net cell reaction, we don't include the electrons as part of that, right? There's no electrons. We balanced out the electrons, we got the net cell reaction. Or the redox reaction, same thing. We balance out the electrons and we write out the redox reaction. So that's not where we're going to use this. That's not going to help us because we don't have electrons in that reaction. What we need to use is the reduction half reaction or the oxidation half reaction. Those are the types of electrochemical equations we need to use so that we can relate the electrons to the, for example, to the mass of the solid electrode, or to, whatever the case might be. So here's our first one here. Here's our first example. It says calculate the mass change. So calculate the mass change for each electrode if a copper aluminum voltaic cell operates with 500 milliamps current for 3 hours. So what we need to do is figure out the mass, okay, change for each electrode. So if you picture copper and aluminum, it says it's a voltaic cell, by the way. Now, we don't have to draw the diagram, but if you wanted to, you know, this is kind of what we're looking at here, right? Let's see, we'll put the anode over here and the cathode over here. And we'll take, let's see. And, of course, in this particular case here, when you think about aluminum and copper electrodes, most simple half cell, of course, is the solid metal with its ion, yes? So in this case here, we would talk about, for example, aluminum and copper, okay, are probably the most, you know, those would be the solid electrodes in this case. Isn't that what it is, copper, aluminum? Is that right? Yeah, copper, aluminum. Copper, aluminum, those would be the solid electrodes here. What else would you have probably? Well, aluminum 3+ and copper 2+ in this case here. Just a very simple half cell design here, okay? When you look at all those things, which one's the most easily reduced? Which one is going to gain electrons most easily? The answer is copper, right? Copper 2+, correct? So we would put that here, of course, copper 2+, and it would add itself onto this copper electrode here, okay? Electrons, of course, would leave the anode and flow this way. It's a voltaic cell, so I don't want to put a power supply in there because they don't need to. They're going to flow spontaneously, right? Spontaneous reaction. And of course, what's going to be losing those electrons? This would be aluminum solid, and it would turn into aluminum 3+ here, aqueous. Okay, and of course you'd have your salt bridge here, like so. Okay, so the big scheme things here, what I'm trying to say to you is this. Okay, it looks like to me, of course, in this voltaic cell, okay, copper 2+ is going to gain electrons to give me copper solid. That would be my reduction half reaction, correct? And over here, I'd say aluminum solid gives me aluminum 3+ and 3 electrons, correct? Okay? Yes? Good? True? Yeah? Huh? Good? Yeah? No? Okay. So, okay, great. Now, it says here, basically, if you go way back up to the top of the question, we need to calculate the mass change for each of those electrodes. Basically, I want to figure out the mass that's going to be plated onto these electrodes, or in some cases taken off, for each electrode in copper. And we have right here 500 milliamps, so that's I. Let's think about what we have here. That's my T there. So let's look at our formula. Way down here. I'm going to do it way down here. Amount of electrons, of course, is IT over F. Let's see. I have I know the amps, I know the time, I know F, I can figure out the amount of electrons that have basically been flowed through this system. So that's what I'm going to do right now. So I'm going to say amount of electrons is equal to I, which was the amps. It's going to have to be changed to amps, of course. It was 500 milliamps, which is 0.5 amps. T is the time in seconds, though, and this is for 3 hours. So 3 hours times 60 minutes in an hour times 60 seconds in a minute. Okay, so basically 3 hours, change it to minutes times 60, times it by another 60 to get into seconds, and that should work out to be 10,800 seconds. Okay. Faraday's law says it's 9.65, or is constant, I should say, is 9.65 times 10 to the 4 coulombs per mole. And what does the amount of electrons equal, therefore, when I calculate that all out? And the answer is 0.05595 moles. Okay? All right. So now I know the amount of electrons that has been basically running through this system here. So I can go back up to here and say, okay, well, if I know how many electrons, basically the amount of electrons that was involved here, I know basically this right here. The amount of electrons was, what did I say, 0.05595 moles. And I also know that this here was 0.05595 moles here as well. Okay, it's basically like finding n, okay, for one of those. And you might say, well, what about the number out in front? Okay, you don't need to worry about that. The number out front, remember, is how you're going to get from here to, for example, here. So you see, people see 2 here and they're like, oh, well, do I have to double this or triple it? And the answer is no. This is the amount of electrons that are flowing through. But to get over to there, for example, if I want to figure out the mass of copper solid, because remember, I want to figure out the mass that was basically plated onto this electrode, or that was added onto the electrode, or taken off the electrode. Well, in this case here, if I want to go from a 2 amount for every 2 moles of electrons, I make 1 mole of copper, basically, right? So to get from there to there, I'm going to have to divide by 2. So I'm going to take this and divide by 2 here to get n here, which is 0.02797 moles. 0.02797 moles. Okay, so it's basically, like I said, this is just stoichiometry with electrons. Okay, now that I know n there, well, gee, I know the molar mass is 63.55 grams per mole. And of course, I can figure out the mass by multiplying those two together, and the mass turns out to be 1.78. So I would expect, due to these electrons flowing from aluminum, the amount of electrons flowing from aluminum to the copper, I'd expect, based on that amount of electrons that are flowing there, I'd expect a 1.78 gram. And this, of course, would be an increase because you are flowing electrons into copper, copper 2+, and those electrons, right, are forming copper solid. So I'd expect that to increase in mass by 1.78 grams. So you could expect 1.78 grams of copper added onto that copper electrode there. Okay? Over here, I know that I have, once again, these amount of electrons flowing from the aluminum here. So once again, that's a 3-to-1 ratio. So to get over to there, I'm going to divide by 3, of course. So divide by 3, I'm going to have here, what is it, 0.01865 moles here. And once again, I know the molar mass, 26.98 grams per mole. And I can figure out from those two, of course, the mass of aluminum that I'd expect to, basically in this case, lose. Because aluminum is turning into aluminum 3+. For every 3 moles of electrons, I'm using 1 mole of aluminum to do that. So multiplying those two together, I'd expect a 0.503 gram decrease in mass of the aluminum electrode. Okay? Good? Yes, no? Okay. So that's just using a little bit of Faraday's law, basically amount of electrons compared to their reduction half reaction, oxidation half reaction. Depends on, of course, that one of those there. We are only going to use reduction or oxidation half reactions because, of course, those are the only ones that involve electrons. So we have to be able to relate that with that. So just keep that in mind as well. That might be something you might have to work backwards from. If we gave you the redox reaction, you might have to just go back to the reduction or oxidation half reaction here. Okay, is that good? Yes. All right, so that's kind of what you're looking at there. All right, next, let's take a look at this one here. A chloralkali cell is an electrolytic cell, so right away, electrolytic, okay, passing energy through it. That involves sodium chloride, basically a solution, so sodium chloride water, For what period of time in hours must a chloralkali cell operate for 350 amps in order to produce 10 kilograms of chlorine? Well, right away, you know, there's some key little things here. If you understand, basically, you know, if you want to save some time here, if you understand that you got to produce chlorine gas, well, really, there's only one redox or reduction or oxidation equation that's going to do that for you. Okay, in order to produce chlorine gas, you need to start with chloride, which actually happens to start right here, right? Look, here's chloride right there, and it says I want to produce chlorine gas. So, gee, I wonder what the equation could possibly be. I'd probably look up, if I were you, two chlorides and chloride and chlorine, and take a look at that. And if I want to produce chlorine gas, I see it right at the top here, Cl2 and 2 electrons would give me 2 chlorides. I want to produce chlorine gas, so I probably should write that backwards, of course, right? Don't forget, this is actually one of those examples. Chlorine, right? Water, which one is most likely to get oxidized? Technically, it's water. But remember, this is one of those chloride examples that we talked about the other day, chloride anomaly, where actually it's the chloride that actually gets oxidized first, because water turns out to be a little bit harder. When you only have chloride, let me get a little piece here. When you only have chloride and water, okay, as possible SOAs, remember, it's technically the chloride that gets oxidized first, right? That's the example we talked about. Once again, you know, out of this, we're not talking about water, we're not talking about sodium, we're only talking about chlorine gas, and you want to produce it. So right away, you should know that, hey, if I take this 2 chlorides here, and if I change that into this here, that's probably what we're looking at there, right? Chlorine gas needs to be produced. You're starting with chloride from that question. That's your only possible equation. And you know what? In the big scheme of things, if you wrote it the other way, you'd probably still get the right answer. Okay? You know, if you wrote it as a reduction as well, still get the same answer. However, it is being produced here. So that's something to keep in mind here. Okay? So it does need to be on that side there. Okay, so there you go. Let's see here. What do we got? It says also we need to calculate the period of time in hours. So the other part here I would say is probably somewhere down here. I'd say, well, amount of electrons is I T over F. And if I want to solve for the period of time, of course, I need to rearrange this formula based on that. So let's see. Up to you guys how you wish to do this. I do my cross multiplication thing because that's what I like. So this times this, and I divide it by that. So hopefully you can come up with this here. Amount of electrons times, F, not that, times F here, divided by, I don't need brackets for the bottom, divided by I, is what you should come up with, hopefully, for that to solve for T. Okay? Do that however you need to, but that's what you need to come up with. All right, so let's take a look here. What do I have? If I want to solve for T here, I need to know amount of electrons. Do I know the amount of electrons yet? No, not yet. Okay. Do I know F? I do know F. That's pretty straightforward, I think. That's 9.65 times 10 to the 4 coulombs per mole. Do I know the I? And I do. It was given to me in the question here somewhere. Where is it here? That's not the right one. 350 amps. So quite a lot there in this case, 350 amps. Okay. What am I doing here? 350. Get in the game here. All right, 350 amps goes there. I don't know the amount of electrons. Okay, so obviously I have enough info, otherwise we can't do the question. Obviously I have enough information to put that in there. I just don't have it yet. The other part, if we go back up to here, I say, okay, there's the amount of electrons right there, but I need some more information because I don't have that. It does say I want to produce 10 kilograms of chlorine. Well, if I produce 10 kilograms or 10,000 grams of chlorine, well, I can use the molar mass to figure out N. So 70.90 grams per mole. I can figure out N here. Works out to be about 141 moles here. Now, that's the amount of chlorine gas that would be produced. Therefore, moving it over to here, I times it by 2, of course, because it is a 1:2 ratio here. So twice the amount of chlorine, or of electrons, I should say. So this works out to be, 282 moles of electrons here. Okay? So that's the amount of electrons that were basically given off in this case here. Well, now I can use that to help me figure out the rest of this question here. So I go back down to here and I say, okay, well, 282 moles of electrons were basically transferred here in this case. So I'm going to put that into there, 282, right? 282, yeah. With Faraday's law and, of course, the number of amps, and I can figure out the time here. Now, the time that you get, of course, you have to remember that when you're using this formula, time is in seconds. So, of course, you're going to get a fairly large number here, 77.5 seconds. Okay? Well, and it says that I want to record this in hours. So, once again, seconds to hours, you're going to have to divide by 60 to get it into minutes, first of all, and then divide it by 60 again to get it into hours. So basically, you're going to divide by 3,600. Yep.
Shouldn't that be like 7,751?
No, I don't think so. 77,705?
Yeah, 77,750.
750?
7,750.
Well, did you use 282 exactly, or did you use the? Well, did you use the unrounded number?
I used that round.
You got this? Okay. Well, let me finish it off here, and I'll grab a calculator and I'll check here. So it should be this, I believe. Okay, just give me a second here. So dividing all this here, getting it into hours, it should work out to be, regardless, okay, just maybe check this one here. It does work out to be 21.6 hours, final answer. Yes, no? Okay. So I'm not sure what, I'll check here right away. But that's what you need to do for that question there, okay? So remember, you're always going to use this, I'll go back down here right away, but you're going to have to use a half reaction, of course, to figure out the amount of electrons. Usually, like I said, in this case, we were given the mass of chlorine. We use the molar mass to get N. We figure out the amount of electrons. Now that we have the amount of electrons, we know Faraday's law, we know the amps that were applied, and we can figure out the time that was applied for. Okay, so maybe let me grab a calculator here. Are we good now? Anyway, okay, so it should be, anyway, you'll get the right answer if you just do all the, don't obviously round or anything like that. I don't know if maybe I'm rounding, maybe you guys are rounding, I don't know, I don't think I did, but whatever. You should get 21.6 at the end there. Okay, you know the steps there, so. All right. Now, one more example here, and of course we talked about this last day. We talked about how you can electroplate. It was some of the notes yesterday, of course, is a common electrolytic application. For example, putting chromium on bumpers, plating a silver spoon, or putting silver on a spoon or a fork or something like that. In this process, a metal ion is reduced, of course. So when it says reduced, of course, to gaining electrons, and that metal atom, of course, would cover the cathode, whatever that happens to be. So general equation looks something like that, whatever the case might be. But here's an example here where you have a copper 2 sulfate solution here, and of course, basically you have this inert electrode, but copper 2 plus, of course, would be added onto here and coat this decorative vase in copper, for example. And a power source would need to be used for this. So then we can talk about, for example, how many amps are required to produce 1.40 grams of copper if we wanted to produce that on this vase, for example. So there we go. Once again, when they talk about amount of electrons, or if they talk about, in this case here, electroplating this, let's see here. Okay. Anytime you see current required to produce for 20 minutes, or if they talk about amps or things like that, you want to be thinking about Faraday's law, of course. So you may want to start with the equation. Doesn't really matter, I guess. At some point, you're going to have to copy that in there. It does say calculate the current. So right away, I know that I'm going to be solving for I here. If I want to solve for I, I'm going to have to do amount of electrons times Faraday's law over T. Okay, is how you would solve for that. And of course, in order to do this, I need to know amount of electrons. I need to know F, which I do know already, by the way. So I might as well write that in there. 9.65 times 10 to the 4 coulombs per mole, so I can put that in right away. The time was 20 minutes. We need to put that into seconds, of course, so 20 minutes into seconds. I would multiply by 60, so it would be 1,200 seconds. Okay, for that case there, 1,200 seconds. And I got 1.40 grams of copper, of course, is what I want to produce, and it goes through a reduction process. So I know that, okay, I do know that copper 2 plus and 2 electrons would be reduced, okay, is how that would work in that case there. And I do know that I want to make 1.40 grams of copper. Now, obviously, you're going to be putting it here. You're not going to make 1.4 grams of copper 2 plus ions. That doesn't make sense. So you have to make the solid here. Molar mass, of course, once again, 63.55 grams per mole. And I can figure out the amount of copper produced, which works out to be about 0.022 moles, roughly. I'm going to move that over to my N here to figure out the amount of electrons, of course. And once again, don't forget that's a 1 to 2 ratio, so I'm going to multiply this one by 2 here, and then use that in my formula, of course. So that works out to be about 0.044 moles, roughly. And that's, of course, what I'm going to put into here. And once again, that number is rounded there, so you want to use the unrounded numbers. Multiplying that all together, basically, okay, 0.044 and the 9.65. You should get a final answer here of 3.54. And remember, when you solve for I in this question, it is in amps. Okay? So you get about 3.54 amps. All right? And that one's maybe even easier than the last one, for example. Probably not as much work as the first one that we looked at either, for that matter. Okay? So that's kind of Faraday's law there. Like I said, anything that has to do with amps or current, time, things like that, you want to consider using this formula here. Okay? Don't forget, of course, reduction or oxidation half reactions. You need to use those because that's obviously the only equations that involve electrons there. So.